Okay, let's jump straight in. We're looking at a new paper called OpenMMReasoner, pushing the frontiers for multimodal reasoning with an open and general recipe.
Yeah, and this one is so important because really the authors are tackling the reproducibility crisis we're seeing in large multimodal models. Their mission is pretty direct.
Which is,
To give us a completely transparent, open source, two-stage training recipe. It starts with supervised fine-tuning, or, SFT, and then it's followed by reinforcement learning, or RL.
and when you say transparent, they're not kidding around. They're releasing everything, the code, the SFT data, the RL data, the whole pipeline.
A little blueprint. It's a really deliberate move to just pull back the curtain on how these very sophisticated reasoning models actually get built.
So the foundation is this massive SFT data set.
A huge one, a really high-quality 874,000 sample SFT cold start dataset. And then they sharpen it, they optimize it with a much smaller but very focused 74,000 sample RL dataset.
And it works. The performance numbers are pretty stark.
Oh, absolutely. This whole recipe delivered an impressive 11.6% average improvement over their baseline, which was the Quen 2.5 VL7B instruct model.
And that's across 9 different benchmarks.
Yeah.
So it's not a fluke. That's a real methodological win.
It really is. That 11.6% jump just shows what happens when you pair a really structured training design with open, high-quality data. It's the reference point the community has kind of been missing.
Okay, so let's unpack that, the transparency. We've seen these big performance gains from closed models, but if nobody knows the recipe, the whole field stalls.
Yeah.
Why was total open sourcing the answer here?
Well, the motivation, it really comes from the text-only world, from LLMs. We've seen these incredible breakthroughs using structured RL methods.
You need things like RLVR.
Exactly. Reinforcement learning with verifiable rewards. Think of models like DeepSeek R1. So the logical next step was to bring that same success over to multimodal models.
So the idea is, if RL makes text models better at logic, it should do the same for models that see images in text. But the problem was that everyone was keeping their data recipes secret.
Precisely. That's the reproducibility barrier. Previous work, even if they said they used SFT or RL, gave you almost no detail on how they built their data sets. You couldn't replicate it. You couldn't understand why it worked.
And OpenMMReasoner just lays it all out.
The entire workflow, the whole blueprint, from how they source the data, how they pick their teacher models, all the way through the SFT cold start and then the optimized RL pipeline.
I get the need for open science, especially for researchers. But doesn't this just sort of hand over the keys to the kingdom? I mean, isn't innovation sometimes born from proprietary, protected methods?
That's a fair argument, but in fundamental research like this, opening up the mechanism allows the entire community to spot the bottlenecks and just speed up progress for everyone.
So the contribution is the recipe, not just some massive, inaccessible model.
Exactly. They believe the community can move faster together with the recipe than any single lab could by keeping it secret.
That makes sense. Let's dig into that foundation then, the SFD stage. They built this huge 874,000 sample data set. What was the philosophy behind getting that much data without, sacrificing quality?
The core philosophy was all about quality assurance through distillation and really intentional scaling. They started with about 103,000 raw questions and put them through 3 really tough stages.
Which were?
Sourcing and formatting, then distillation and scaling with a much stronger teacher model, and finally, domain mixing.
Okay, so the teacher model selection is key. If you're distilling knowledge, you need a powerful source.
Absolutely. And they picked Quen 3 VL235B Instruct as their optimal teacher. It consistently gave them an average performance gain of at least 4.5 points over other baselines.
And this teacher isn't just giving answers, it's showing its work.
That's the crucial part. They only kept samples that passed both a rule-based validator and an LLM as judge check. They weren't just checking if the final answer was right, they were checking the quality of the explanation.
This is where we get to one of the most interesting findings in the paper, for me at least, the whole idea of answer diversity. They found that getting more verified answers for the same question was a huge performance driver.
This is so critical. We always think about question diversity, right? Get more topics, more images. But they showed that for really complex reasoning, the model needs to see multiple valid ways to get to the same answer.
They tested this pretty rigorously.
They did. They scaled the sampling from 1 answer per question all the way up to 8.
Can you give us an analogy for that? Why is having 8 answers to one question better than just having 8 different questions?
Think of it like training a musician. You can teach them to play a song one specific way, note for note. They'll be good at that one song.
But they can't improvise.
Right. But if you show them 8 different valid interpretations of that same song, different timings, different emotional deliveries, they learn the underlying musical theory. They become robust, flexible, they can generalize.
And the data backs that up.
It does. The times 8 configuration with 8 verified answers per question pushed the average performance up from 50.5 to 55.2. That's a huge jump, and it all comes from teaching generalization, not memorization.
Okay, now for the part that seems to fly in the face of everything data scientists are taught, filtering. You're telling me that when they tried to clean up the data, remove the hard stuff, the weird outliers' performance actually went down.
It did. It's so counterintuitive. They tried filtering based on difficulty, based on the length of the answer, and both methods hurt performance. The conclusion is pretty profound.
Which is that over-filtering is a bad thing.
It's detrimental. You lose so much data set diversity that it outweighs any benefit you get from having a cleaner or more consistent data set.
So for complex reasoning, diversity trumps consistency. The model needs to see the messy stuff to learn how to handle the real world.
That's it exactly. Their final SFT recipe, after that first strong validation check, has a strict no-filtering policy.
Okay, so they have this high-quality general data set. Then they move to domain mixing. How did they use specialized data to broaden the model's skills?
They knew that general visual question answering wasn't enough for true reasoning, so they intentionally mixed in very specific math reasoning data.
Image-based and text-based.
Both. They used MMR1 for image-based math and MiroMind M1 for text-based math. And this cross-domain mixing, it just consistently improved the model's final reasoning ability. That final 874,000 sample data set became the foundation for the next phase.
Which is the RL phase. So we've gone from building the raw knowledge with SFT to now sharpening those skills, making the model more robust.
Correct. And for this, they used a much smaller 74,000 sample data set that was purely focused on complex problem solving. Stuff from Eureka, VRL, hard math problems, puzzles.
Let's talk about the algorithm choice here. This is pretty deep in the weeds, but it's important. They compared 3, GSPO, DPO, and GRPO. Why did GSPO come out on top?
It all comes down to training stability. When you're dealing with these long, complex chains of reasoning, the training process can just collapse.
And that's what happened with the others?
To an extent, yes. DPO, for instance, it suffered from what they call early entropy collapse. Think of it as learning too fast and getting stuck. It optimized for small, local things like fixing grammar word by word, and it never learned to see the bigger picture.
It got stuck in a rut, basically.
Precisely. GSPO, that's Group Sequence Policy Optimization, it avoids that trap. Instead of optimizing token by token, it optimizes the entire reasoning sequence as a whole.
So it's like editing an essay for its overall argument, not just for spelling mistakes.
Perfect analogy. And that sequence-level approach gave it much better stability, it converged faster, and it just got higher rewards in the end.
Stability is everything. So beyond the algorithm, let's look at the reward function. They had to balance accuracy, getting the right answer, with format consistency, making it look nice. How'd they weigh those?
This was a delicate balance. They found if you reward formatting too much, the model becomes very polite, but less accurate.
It learns to be a good student, but not a genius.
Right. So they found that a really low format reward coefficient, a lambda of 0.1, gave the best results. It's a clear signal. Prioritize getting the right answer above all else.
So the takeaway is genius over politeness.
During this optimization phase, absolutely.
Okay, that clarifies the reward. What about the practical side of running RL, the rollouts? What did they learn about balancing, exploration versus stability?
2 really critical lessons. First, high temperatures are bad. A rollout temperature of, say, 1.4, which encourages a lot of random exploration, it just caused the training to become unstable and diverge.
So too much creativity is counterproductive.
In this context, yes. And the second lesson was about sampling size. They found that increasing the rollout count, the number of samples they took for each update from 8 to 16, made a huge difference.
It improves stability across the board.
Significantly. For an unstable algorithm like DAPO, that increase from 8 to 16 was the only thing that prevented it from collapsing entirely in the late stages of training.
More samples just smooths out the noise, gives you a more reliable direction. That feels intuitive.
It does. And all of this leads to a major practical win for their whole approach. Reasoning efficiency.
Right, the token budget. OpenMMReasoner gets better answers while using way fewer tokens than its competitors. That's huge for actually deploying these things.
It's massive. A model that takes twice as long to think costs twice as much to run. They compared it to a model called OpenMMReasoner, or OVR.
And the difference was what?
It was dramatic. On the MathVision benchmark, OVR used an average of almost 18,000 tokens to get an answer. OpenMMReasoner, using an overlength penalty strategy during RL, got a better score using less than 10,000 tokens.
Wow, nearly half the cost and latency. So they've effectively cured the model of its tendency to overthink.
Exactly. And that efficiency is just as important as the raw accuracy for anyone wanting to use this in the real world.
So let's tie it all together. The final model, OMR7B. What were the headline results?
It achieved state-of-the-art on several really hard benchmarks. We're talking 79.5 on MathVista, 34.9 on WeMath, and 38.8 on MathVerse. It just confirms that the whole SFT plus RL recipe works.
Okay, but this next finding is the one that really blew my mind, the cross-domain transfer. You're saying that training this model on images and text actually made it better at tasks that were only text.
It did, and this is probably the most exciting academic result in the paper. They tracked its performance on purely textual benchmarks, like A and GPQA Diamond, and as the multimodal RL training progressed, its scores on those text-only tasks just kept climbing steadily.
So the skill of reasoning, of breaking down a problem, analyzing it, that it learned from multimodal data, that skill just transferred back to pure language.
It suggests we're optimizing a shared fundamental cognitive mechanism in the model. We're teaching it how to reason, not just how to solve a specific type of puzzle.
And they saw qualitative evidence for this too, right? The whole reflection words analysis.
Yes. This is fascinating.
Yeah.
They looked at the actual text the model was generating during RL, and as the reward went up, the model started using more of what they call reflection words.
What are reflection words?
They're markers of an internal monologue. Words like let, wait, perhaps, or let me think. The model is literally learning to talk itself through the problem.
So the RL setup is actively rewarding the model for showing its work, for having a more structured thought process.
That's what it looks like. We're incentivizing it to engage in more explicit, structured reasoning, and that behavior leads to better answers.
Okay, so to wrap up, let's list the 5 big empirical takeaways for anyone trying to build these models.
First, for this kind of multimodal RL, GSPO is your best bet for stability. Second, answer diversity is king. More verified paths to an answer beats just more questions. A strong teacher model is crucial for that initial cold start quality. Fourth, mixing and cross-domain data is essential for generalization. And fifth, you have to actively manage token efficiency with penalties, or your model will overthink and become too expensive.
So this paper really does provide a critical blueprint. It proves that a transparent, high-quality data recipe combined with stable RL optimization is the path forward for multimodal reasoning.
For sure. And the authors are upfront about the limitations. They mainly focused on one model family, Quinn, and one modality, images. The next step is to see if this recipe works for other models and for things like video and audio.
Which brings us to our final thought to leave you with. Given that this RL recipe didn't just improve accuracy, but it actively encouraged the model to use reflection cues like, let me think. It rewarded a kind of structured self-talk. We have to ask a bigger question.
Are we just building more capable models? Or are we accidentally discovering that the very process of making them better reasoners also makes their thought processes more explainable?
Could explainability be an emergent property, a positive side effect of just rewarding good structured logic?